Hey, Math 30-1s. We're going to go over our worksheets here. We're going to do worksheet number 1. What is the value of this expression? Now, the reason I'm asking this question is because 50 factorial, or actually, is it true? 50 factorial might be able to be possible in this, right? Is 50 factorial too large, or is it? No, it's not too large. You can technically plug in your calculator, but you know what? I'm going to do this kind of the old-fashioned way. What if I didn't have a factorial button in my calculator? What would I do here? Well, I would expand out the bigger of the factorials. So let's expand out that 51. 49. If I couldn't do the factorial button, this is what I would do. So keep on reducing down by 1 each time. I'm going to stop at 47 factorial because 47 factorial is also on the denominator. So that reduces out. And then you can just plug this into your calculator. 3 factorial is technically 6. So there's a 6 on the bottom. 50 times 59 times 58 is 11,000. Nope, 117,600. And then we just divide it by 6. And I get 19,600. I'm pretty sure you could have got that using your calculator otherwise too, but I like doing it this way because that might be more useful to solving kind of questions like this, except for this would be a quartic function. That's fine. We'll deal with that in a bit when we get to that question. How many ways can you rearrange the letters? All the letters in each of these words. Now, it's key is all the letters because there is repetition. It's hard to do repetition if you're picking just a very particular number of letters, like 3 or 2 letters, because you don't know if you picked 2 O's or you picked only 1 O in this case, because it gets a little bit tricky. Then you have to take the cases. It's possible. It's just a little bit trickier to do. 1, 2, 3, 4, 5, 6, 7. There's 7 letters, and there are 2 O's. So I'm going to divide by 2 factorial there. I don't think anything. Oh, it's 2 S's as well, right? Totally forgot this capital S and little s. I'm assuming that if these are Scrabble letters, everything would be capital letters anyway. So they are considered the same. So 7 factorial. If I get to factorial here, divided by 2 factorial times 2 factorial, which is technically 4. So there are 1,260 ways to do that. Now the word arrangement, 1, 2, 3, 6, 7, 8, 9, 10, 11. Okay, so it's 11 factorial, and there are 2 A's, 2 R's. That's a lot. There's 2 N's. Yeah. G is only 1 G. There are 2 E's. Okay. Only 1 M. 1 T. You already dealt with the N's already. A's are, yeah, seems like, I think that's it. Hopefully I didn't miss any letters. Sometimes it's tricky to see the repetitions. 2 times 2 times 2 times 2. So there are, rather than being 39 million ways. Hello.
Hi.
Okay. So let's move this up here. Next one. Oh yes, I gave you the answer here. So rather than being 39 million, it's only about 2 million because of the repetition, which I hope I didn't miss any of the repetition there. I think everything's just 2s. Yeah. Okay. So 7 students are running for an election to be student council president. How many ways can these 7 students be listed on the ballot? Yeah, so wouldn't that just be 7? Yeah. So there's only 7 ways to list the kids on the ballot? Or is there lots of different ways? Yeah, you're right. Never mind. There's lots of different ways to list all 7. Right? Now, if order didn't matter, there'd only be 1 way to do it. You put all 7 on the ballot, and that's it. But if the order in which you put them, sometimes it's important when you're doing elections. You think, if you're just going to vote because someone just told you to vote, you might just pick the first person on the ballot, right? Or you might be that guy who just says, I want to pick the guy right in the middle, right? So maybe the order does matter. So in this case, I have 7, P7. So all the kids are going to be used. And this would be just like 7, 6, 5, 4, 3, 2, 1. All the way down, putting all the kids on the ballot. Or you could say 7 factorial. Like, there's a lot of different ways to say the same thing. So 7 math factorial. So there are 5,040 different ways to rearrange the 7 kids on the ballot. Now, here it doesn't specify solve algebraically. I'm not going to solve this one algebraically because I'm going to get like a quartic function. Actually, I'm going to get to a certain point where I'm just going to stop trying to solve it algebraically. So I'm going to start by writing out the formula. Right? So I'm going to use the permutation formula here. I'm going to then start expanding out the top piece. Oops. Oh, I missed the 2. Oops. Because the top one's the larger one, so I'm going to expand that one out. Stop at the n minus 4 factorial because that's just going to reduce what's on the bottom because it's the same number. And now what I'm going to have here is a quartic function. So I'm not going to multiply any of this out. What I'm going to do is I'm going to graph the left-hand side, graph the right-hand side, and then from graph, determine my solution. Okay? So from the graph, n is equal to, and I'm just going to plug in my calculator here. So we're just using x's instead here. So x minus 1, x minus 2, x minus 3. Yep. I'm going to go to 900-ish. Yeah, let's do that. Let's see what this graph looks like. It's going to be quartic, so I might have 2 solutions. So yeah, so I'm going to look at my graph there. So it's a positive quartic graph, so it's opening upwards. You can see there my line there crosses twice, but I'm not going to want to do the negative answer here because the negative answer wouldn't make sense in the question. You kind of have negative things. So I'm just going to do it with a positive answer. Second trace, or second trace, number 5. Enter. Negative 4, that's not going to be second trace. Enter. What would that guess be? Like 8-ish? No, 7. Okay. So I get 7 or negative 4. Negative 4 doesn't work, so 7 is my only answer here. All right, so for this next question here, we are going to go, we're just going to guess, check, and revise because there's only a limited number I can actually have here. I have to go from 0 to 5. So I'm just going to go 5p. I probably won't go 0. It doesn't make sense to be 0. But 5p1, 5p2, 5p3, and just kind of go down until I get 20. Right? There's really only so many, and there's no real point to trying to solve it any other way. You could try to graph it. Just tried my calculator just recently, and it doesn't let me graph permutations nicely. But if I just go through and guess, my second guess there, the 5p2 ends up being 20. So the first one ends up being 5, which is not going to be my answer. This one ends up being 20, so n is equal to 2. Now, I don't know how you would try to graph this. Maybe you can graph it using factorial notation. Let's be 5 minus r factorial over 20. Let me just double check, see maybe you can graph this with factorials. Yeah, so I realize you can't graph these because factorial notations are very stickler, like they have to be whole numbers. So if you try to graph it, you don't get too much on your graph. But if you do go to your table, you can find out, so when n is equal to 2, sorry, this got blurry right there. You get 20, 20. So you can get to your table, but there's nothing in between because factorials don't really work too well for strange numbers. So having like a half or 0.6 or something like that in here doesn't make this work nicely. So I'm just going to guess check and revise and get it to work, and then you got 2 here. How many 7-letter arrangements can be made from using all of the letters L, M, N, O, P, and I, and U? Okay, so how many? There's 7 letters there. So how many can? 7 factorial, or 7p7, et cetera, et cetera. So there's lots of different ways. I think we did this very similar question up here. We have 7 students running this, so 5,040. 5,040. Okay. Of these, how many begin and end with a vowel? So I'm going to use my counting principle here to do this. So how many vowels do I have? I have I, O, and U. So I have 3. I have 2. And then the other vowel, I'm just going to mix in with the consonants there. 1, 2, 3, 4, 5. And all of this through here is going to be 5 factorial. Okay. So let's see what we have here. So 3 times 2 times 5 factorial. So 6 times 5 factorial, which is actually just 6 factorial. Okay, that's pretty cool. So 720. Cool. How many of these begin with a consonant and end with a vowel? Okay, so let's do the same thing. 2, 5, 6, 7. Okay. I'm going to begin with a consonant. So my first letter has to be a consonant. 1, 2, 3, 4 of them here. And I only have 3 vowels over here. And then I have all the other letters from here to here. Right? So this would be 12 times 5 factorial. Could have said them mentally because it's twice the size of the other one, but whatever. Cool. Yeah, awesome. In a fitness club, plans to issue members codes. The first character and the third character can be different letters chosen, or the first and third character can be different letters from A to M inclusive. The other 3 characters must be different digits from 1 to 9 inclusive. What is the maximum number of members that you have? Inclusive means they include those numbers. If they said exclusive, means you're not including those numbers. So we got a 5-digit code. 1, 2, 3, 4, 5. The first have to be different letters from A through M. So A through M. How many letters are A through M? Okay. A, B, C, D, E, F, G, H, I, J, K, L, M, N. 14 letters. There's only 14 letters. Okay. Yeah, okay. So we have 14 choices, options for the first letter. Because it has to be different, there's 1 less for this third one. And then they must be different digits for the other 3 characters here we have here. So I have 1 through 9. Okay, so that's only 9 digits because they're not including 0 here. So 9, but it has to be a different one, so it has to be 8, and then it has to be 7. Okay. So I'm just going to multiply those together. So they can have 91,728 members. How many ways can we rearrange all the letters of the word parallelogram? It's a lot of repeating the digits here. So parallelogram, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah, 13 letters. Okay, so 13 factorial is going to be a pretty big number. And then I'm going to have to divide by all of the different repetition that we have here. So how many A's or how many P's? Do we have any other P's? So I'm going to just cross that P off for now. Okay, how many A's are there? There are 1, 2, 3 A's. So we have 3 factorial ways of rearranging those. So 6 ways. So I'm just going to cross the A's off. How many R's? Okay, we have 2 R's. Cross the R's off. Okay. 1, 2, 3 L's. So 3 factorial ways of rearranging those. E's. Okay, I only have one E. If you want to put 1 factorial, you can. It doesn't really do anything. We only have 1 O, 1 G, and 1 M. Okay. Thought there's going to be a lot more repetition than that. So 13 factorial would be 6 billion ways to rearrange it. 6.2 billion ways. That's a lot of ways to rearrange letters. But I do have a bunch of repetition here, so I'm just going to divide out those repetitions. Still a lot. So there are 86 million ways, 486,400 ways of rearranging the letters, a parallelogram, so it's quite a bit. How many of these have all of the A's together? Okay, so all of the A's, how many A's do we have? 1, 2, 3 A's. Okay. So this is going to be, you can think of the A's like how we would do for the photo kind of pictures. We have like this kind of 3-headed monster where all the A's have to be together. So you consider all the A's to be one letter. If I consider all the A's to be one letter, I have 11 letters. I'm not going to subtract 3 out. I can subtract 3 out, but then I have to put 1 back in because they're all one letter now. So there are 11 letters here. Okay. That's one way to do it. But then all the other letters, you got to think of the repetition for the other letters. So I'm not going to multiply it by like 3 factorial because I'm just going to divide by 3 factorial later on. Like how many different ways can I rearrange the A's? I can just divide that out. So I'm not going to worry about that. But I still have to worry about the 2 factorial, 3 factorial from the L's and the, what were the other letters? The L and the R's. So now it's going to be 11 factorial divided by 2 and 3 factorials. Okay, let's see what we have here. It's not going to be as big. Only 3 million ways. Of the 86 million, only 3,326,400 ways have all the A's together. How many ways, how many arrangements of all of the L's, A's, and R's, so all the ones that are repeating each other, how many ways are they being repeated together? Okay, or together. All the A's, L's, all the A's, and all the R's together. Ooh, this is why I don't really like permutations because the wording can be weird. Am I putting all of those letters together as one thing? Or can the L's and the R's be separated? Maybe I'll just write up both and think about the different situations. Okay. If all the L's, A's, and R's have to be together, then I can treat them all as one thing, right? Then I'll have to worry about how they can mix up as well within their groupings. This is going to be an interesting question. All the L's, the A's, and the R's together. Okay, how many L's, A's, and R's do we have? One, two. Oh yeah, here. Never mind. I have them right here. So I have three A's, 2 R's, and 3 L's. So I have 1, 2, 3, 4, 5, 6, 7. I have 8 letters. There's I have 8 letters. So I'm going to have 8 letters right here. They're all going to be together. So there's going to be 8 of those letters in there. The R's, the L's, and the A's. So I can think of this as 8 factorial ways of rearranging those letters. But there is repetition in there. So there's going to be 3 factorial, 2 factorial, 3 factorial again. Okay. Okay, looking pretty good. But I don't have to have them all at the beginning. They could be in different spots around here. So how many letters are left of the 8 letters? So there's 13 in total, minus 8. So there are 5 letters left here, right? 5 letters left. So I'm going to have 5 factorials. These are all the other letters that we have. But then I could put these in different spots. Like if I had to group them all together, I could put them in different spots as you go through. Yeah, okay. So I could put them in 6 different spots. I'm gonna have to times this by 6. Okay. So let's go through that. That's gonna be a tricky one. This is a pretty tricky question. Divided by 6 times 2. So it's not that many though. So 403,200 ways. Okay. That's if they're all stuck together. What if they weren't stuck together? Right? So if they weren't stuck together, I can have it this way. All the L's, all the A's, all the R's, okay? Then I have the 5 factorial letters, right? How can I rearrange all of these? Right? So what you could do here, you can go like these L's, right? So this would be 3 factorial divided by 3 factorial, 2 factorial divided by 2 factorial, et cetera. Because how many ways can I rearrange the L's, and all the L's are the same. So it's really only one way for each of these. So all the L's are considered like one letter. All the A's are considered to be one letter. It's like very similar to question B. But now what if I could separate them just slightly? What if I could put some letters in between them? Or put all the R's between the L's and the A's and stuff? But that'll be a different orientation. So to do this, I mean 1, 2, 3, plus the 5. So really there's only 8 factorial ways of doing this. That's it. Because you could treat them all as individual letters. 8 factorial ways of doing this. So 40,320 ways to do that. Is that right? Seems a bit low for some reason. Why is it a bit low? What am I missing? What am I missing? Do. All right, so it makes sense it would be a bit lower just because of the way it is, because I can't have the A's in between all the L's. So I can't mix them up. I can't jumble up like C. I can jumble them up as long as they're all together. Yeah, so that makes sense that there'd be more on this side than this side over here. All right, there we go. So I'll see you in the next video. Bye.